It's a pleasure to be here. In all these years, this is the first time I've actually been at Rutgers University. There were possibilities that I couldn't make in the past. So I'm going to talk about something rather fundamental, and I'm going to adopt a somewhat different problem model than you've been seeing, although, let's see, that's going to go to the right. Yes, so I'm going to propose a kind of model. You'll see some similarity. There are other versions of this, but let's just focus on this. So I have f and a little g, and then I have a mapping in there, but I'm not assuming convexity here except to the function g. So I have a sort of a block decomposable type of structure to begin with. These xj's are blocks of things in different spaces. This could be infinite dimensional. I'm just simplifying things here. And I'm not assuming, and the functions little f are just lower semi-continuous. The mappings big F I'm going to assume are smooth in some degree. And the function g I'm assuming convex. Now, for the purpose of this talk, I'll also have it be positively homogeneous because it simplifies things. I can do the general convex case, but it just looks a little messier and it's not so good for the slides in the short time I have. So examples are a little different from what you're thinking. Everybody could understand that this g could be the indicator of a cone. And then I'm looking at constraints with some possibility of decomposition that I'm trying to get. But what you don't see much is that g could be something else, like a norm. This is also positive homogeneous. So there's so many optimization algorithms now that involve regularizing terms. So you could think of it as something like that. But there are many more possibilities included in this. And as I say, g could be a general convex function. Now, what's also a little different about this is that I have a subspace S in here. It could be the whole space. I mean, it just drops out, obviously. But another idea of that subspace, it could be the subspace, as seen down in here, where I ask all the x's to be the same. Then I would be looking at a splitting model. All the x's are the same. But what else could it be? There are people here who've done progressive hedging. This could be the non-anticipative subspace in stochastic programming. And there are many other things it could be. I'm thinking of like linear relations like Kirchhoff's laws in a network. Or they could be dynamical relations in a multi-period problem which relate what's coming back and forth between different periods. So some sort of underlying linear relations. And I'm thinking of that as a coupling space, and G is a coupling term. And I'm going to do decoupling. So this could be, of course, a convex problem. And then everything could be global. So suppose, for example, you take the function capital F's to be A mappings that are linear, affine. And you take the little f's to be linear. Then I'd have a convex program there. But there are other versions of convexity. I could have, for example, the fj's are somehow convex mappings, and the f is non-decreasing. Then you also get the way actually to capture what is a convex and non-convex problem is through the Lagrangian, but I don't really have time to go through it. But there's a huge area of this which is convex, but that's not what I'm going to aim at. What I'm going to talk to you about today, although it's in the background, everything would be global, is how I'm going to be able to do local non-convex things, where I can understand that I will converge not just to a Kuhn-Tucker point, but to a locally optimal solution. Because I'm going to involve a technique which is called elicitation of convexity or monotonicity that will do the trick. And it's very closely related to local optimality conditions of a second order kind, but which are new, which have not been looked at. So first of all, let me show you a trick which I don't see anybody else use. And it's simpler. This trick is simpler in this homogeneous case, but I can do it more generally. So I'm looking at that coupling term, and I suppose I want that less than or equal an alpha. I can rewrite this equivalently, I'm claiming. There's actually a very simple proof to it. It's just that people haven't really thought of it this way. That I can write it as, oh, there's something missing here, something obviously missing. What I'm supposed to have here at the end is a minus or plus uj in those other terms. So it should be fj plus a uj in those other little terms over there. So, and then those uj's add up to 0. So basically, I'm able to take that thing and split it into a sum. So now I have a coupling space because I have some additional variables, uj, and they satisfy linear relationships. I can add that to my coupling space as linear relations. So I'm now looking, I put a bar over it for this purpose. I'm looking at the original variables and the new variables, such that the original variables belong to the subspace S, and the u's equal 0. And then we need, in every case, for my method, we're going to need the complementary space. And here, of course, it would be the complement of S, and then the complement of the u's adding up to 0 is that the y's should all be the same. This is a kind of simple duality that occurs over and over again. So through that trick, which I had left out the u on the final lower right corner of that upper panel, I can rewrite the problem equivalently with the extra variables so it becomes separable. Separable for j. And so I'm going to minimize this separable function over a subspace. And I've gotten it this way. So I have a function phi of all those variables, which I'm writing as a sum of terms, one for each index. And now I'm going to leave this problem for a moment and discuss how I would minimize a function phi over a subspace without necessarily assuming convexity and get these local ideas going. So let's look at this. So I'm interested in minimizing, I'm only assuming it's lower semi-continuous on a subspace. And there's a first order condition for that, which is that you're looking at a point. So I change the notation so I can switch back to the x's and u's later. I have a w in this. This is just some subspace. Has nothing to do with the earlier one. I have a w in the subspace, and there should be a subgradient z at that w, such z bar, such that z bar belongs to the orthogonal complement. And this is obvious condition, but you can especially see it. Suppose that the function phi is really a smooth function. So we're minimizing some differentiable function over the subspace. Then the optimality condition should be that the gradient is orthogonal to the subspace. This is the obvious condition, and that's a subgradient version for it. And then looking at that local, that's like a first order condition. Is it necessary, sufficient? I don't care at the moment. Under some cases, but I could say, I would like to solve, think of it like a Kuhn-Tucker condition. I would like to solve a first order condition. Suppose I had that limited point of view in this situation. Then this is what I've been calling a linkage problem. And similar to what John Spingarn did in his work long ago with a partial inverse method involving a monotone mapping. You could think of it as a problem involving a mapping. Here it's the graph of a subgradient mapping. Given a function phi, that is given a subgradient mapping, and S, I want to find a pair that belongs to the graph of that, and with the one in the S and the other in the complementary space. And so you could think of trying to solve that. So suppose phi is convex. I have something monotone. And then I would be looking at the kind of problem that Spingarn looked at. Now let me just remind you of subgradients. So Radu just gave you the version of the definitions that Boris Moravovich has adopted, but the ones in my variational analysis book, which came earlier, had different terminology. But the interesting thing is Boris didn't like to call things regular subgradients because of misunderstanding of English. He thought regular should mean something very special, but in English it means ordinary. I'll have regular coffee, something like that. Regular gasoline. And he thought it meant something very special, so he didn't like it, so he changed it to... Anyway, so here, first of all, we have a definition. I don't have to use a complicated notation because everybody here understands a little o term. So the definition of a regular subgradient is, it's just like the definition in convex analysis, except you have this error term, right? And then what I call the general subgradients, or just subgradients. And notice here for the regular ones, I have a little hat. And Radu had that too. Boris has that too in his definition in his book. And he was dealing with infinite dimensions too. And I do deal with infinite dimensions, but I'm happy just with Hilbert spaces because I want to use all this quadratic stuff. And that's where quadratic things live, in Hilbert spaces. So then the general subgradient you get by taking limits. And a feature to keep in mind here. So you're looking at a limit of things which are regular subgradients, and another feature you need because we only have a lower semi-continuous function. It could be discontinuous. So in general, you need the condition also that the function values would converge. For some functions. Some cases, you don't need that. All right, that's the first order condition. But what's critical here is something about second order and elicitation. So here's the critical idea. So remember, I want to minimize a function phi over subspace S. But there's no change in the problem if I add to that function a multiple of the distance squared from the subspace. Because the function agrees on the subspace, right? There's nothing added. It's like, and I'm not passing to a penalty formulation. I'm still minimizing over the subspace. But adding that doesn't change the problem. However, it could change properties of the function. That could be very beneficial. And here's what comes out of it, which is a very general, this is an extremely general context, minimizing a lower semi-continuous function over a subspace. There's a second order, I call it second order because there's convexity behind it. Second order variational sufficient condition. And this is assuming I have the first order. I'm looking at a pair that has the first order condition. So this takes a little bit of understanding. It's maybe hard to understand this at the beginning. But the idea is that I can have below the function phi, I can have a function c, which for all purposes that I'm interested in will do the same thing as a function phi, but c is convex. So the idea is that I will have this function so that its graph, well, let's look at this graph of t sub e epsilon. E is this elicitation parameter. Maybe I can make it bigger and bigger and good things will happen. So E. And epsilon is just some neighborhood type effect. And I'm looking at the pairs, the things in that subgradients of that phi sub e, very closely related to the ones of phi that we don't have to care what they are right now, which I have that, the function values are near also. And that graph is a graph of a certain set-valued mapping. And that's the mapping we may need to deal with. Well, and so that the subgradients of the convex function agree with that, and the function value of c agrees with the function value of this elicited phi sub e, at all those points. So it's basically that by making e big enough, then near enough with epsilon, I will get everything about phi, c can do better, something like that. All right, now here's this really interesting thing. I worked very hard on this part. In fact, it took me months, and I didn't get quite all the way with it, but it's good enough. So under this condition, first of all, you should understand why would that mean that why is it a sufficient condition? Because according to this, finding a subgradient of this phi sub e is going to be the same as finding a subgradient of this phi sub e on S. It won't make any difference on the subspace. But on the other end, it's going to coincide with this graph of the convex function. So I'm going to have the first order condition satisfied for a convex function that's down below. So the convex function will have a minimum there, but the function values agree. And so this is sufficient condition for the original thing. I'll give you an example in a minute. Anyway, here's the thing. This implies that that truncated mapping here, an elicited mapping, is maximum monotone locally around a point. This is going to be the key to applying the proximal point algorithm in the background, which can be done just locally. You don't have to be global with a proximal point algorithm, as Teemu Pennanen, a former student of mine, showed. And now the thing I was unable to get completely around is that I have to assume here that this z is a regular subgradient. I don't think that's really necessary, but I was just unable to prove it. It was a very long, complicated proof just to get this regular case. All right, now here's an example of this again. Now suppose I'm minimizing a function over a subspace, just to get the idea of it. Suppose it's a C2 function. And then this first order condition is simply that this z bar is a gradient, and the gradient is perpendicular to the space. And then if the Hessian of that function is positive definite relative to the subspace, then it's well known in augmented Lagrangian theory, then you can get your elicitation parameter high enough to make this, if I added that thing, the distance from the, if I added that term, that phi e would be, have a global minimum at that point. So if instead I wanted phi to be convex, in effect I'd be asking that all the Hessians would be positive semi-definite at all points of the subspace. But I just need positive definiteness at one point. So there's a very definite difference, but I'm trying to convince you in this little way that this is actually a very natural condition. This is the way to express it very generally, somehow the most natural condition that would apply in this area. Okay, now here would be the algorithm in this case. Now I call this progressive decoupling because it's inspired by the progressive hedging algorithm, but you can't use the word hedging when it isn't something stochastic. It doesn't make sense anymore. So this is progressive hedging, but I changed the name. Progressive decoupling to be more general. And here's how it comes out. So, this is just for minimizing this phi. So at any given iteration, I have a primal and dual pair, and I use new to mark the iterations. And then what I will do is minimize a regularized function. You see, it's the original function tilted. I subtract a term. The z is going to be something like a multiplier for the linear constraint that makes you stay in the subspace. I'm tilting it and adding a proximal term. And the tilt and the proximal location, those are the two things that are given at the beginning of the iteration. So I solve that, and then I project. It's a general term for this. I project this hat thing onto this underlying subspace, and then I make an update. And this is the only place that the elicitation parameter comes in here. It looks like a relaxation of a Lagrangian, augmented Lagrangian update. And it should be high enough. So what does high enough mean? Well, I'm thinking that high in the sense of that second order condition being, second order sufficient condition being satisfied, variational condition. And then what's the convergence? Okay, now this is, again, it's a little complicated to, it's not too hard to understand, but it's a little complicated to know exactly how you would implement it. So first of all, I'm going to assume that there are some tilde elements that satisfy the first order condition and the second order variational condition, the sufficient condition, at that tilde pair. Then there will be a neighborhood of that tilde pair such that if I initiate the algorithm in that neighborhood, all local algorithms have to be initiated close enough, let's say. If I initiate it in there, then forever it will stay in there if I'm careful. Forever will stay in there. And what I can guarantee is there's a neighborhood W here that's fixed. And on that neighborhood, the things I have will always have unique local minimizers. And then that pair will actually converge to some pair that not only satisfies the first order condition, but is in fact gives the local argmin on that W. So rather than going for a Kuden-Tucker point, what this does, knowing that the variational sufficient condition is satisfied, I will get convergence to, the trouble is I can't tell you how I would know when I'm in that neighborhood. But that's not, a lot of things. Newton's method. How do you know you're near enough? But certain things take over when you're near enough, and at this stage, this is all I can say about that. But it would converge. So now let's get back to the original problem. So here we were minimizing that function up there over a particular subspace. And there was that subspace S bar, and there was its complement. So I just apply that algorithm, and it comes out this way. This is the first version. Then I'm going to get to an augmented Lagrangian version. So at a given iteration, I have primal and dual elements. And then I'm going to decompose in that for each index j, I'm going to solve a subproblem. Each index j, I have a function phi j nu. And it's obtained by looking at this term, tilting it, I subtract two linear terms, and adding two proximal terms. And you remember the proximal, the UJs add up to 0. And then if I take the average of the U's that I get out, then I get this update. I project onto the subspace S, and then I get a very simple update of the U, and then I get these Lagrange, augmented Lagrangian type updates that have this elicitation parameter come in there. And again, the E is supposed to, this is based on the idea that we're trusting that we're near enough to a place where the second order sufficient condition is satisfied, and this E enters into that being satisfied, and then we have to be that high, and R has to be higher. And but I could have E even higher than need, and then I get under those local sufficiency conditions, there will be local conversions just as I described. And now, of course, this could be specialized to the splitting case, the stochastic programming case. All those are specializations of the thing. Now let's look at what happens with augmented Lagrangians. A lot of people think augmented Lagrangians are just something where you add a square of some equation term, but it's not that way at all. It's a far more general idea. And you can find that in my my variational analysis book, for example. Augmented Lagrangians much more generally. So here's what I want to think of for the moment: a subproblem in which I have, for a single index, j, I'm going to minimize a term that looks like that, fj plus g. G is the same here. It doesn't depend on j. And then I have, but I'm shifting the s. Then f nu now is the old f shifted by the current shift term, u nu sub j. So I look at the subproblem. What if I wanted to minimize that in xj? And now here's where it's a little simpler, that I'm asking that G be lower semi-continuous convex and positively homogeneous, because we know those are the support functions of closed convex sets. So I can say that the conjugate of G is indicator of some closed convex set Y. So for example, if G was the indicator of a cone K, then I would be looking at the polar cone Y. But what if G is a norm? Well, Y would be the unit ball for the dual norm. But there are many, many things that fit into this. And again, I could do all of that just with convexity. And then there's the augmented Lagrangian. And the augmented Lagrangian comes out like this, starting to look like some of the primal dual things we have. We have, this is just for J, for this little subproblem for a single index, I have a Lagrangian that looks like that, and now minus indicator function. And then the corresponding augmented Lagrangian with a parameter R, you get that by the general formula. There's a whole theory of just how you would get that. And what it comes out to, it looks like this. This is, again, it's simpler because I took G to be positively homogeneous. You can recognize in the beginning, oops, seem to have repeated a term. Well, I can see things to fix. I seem to put a term in here twice. That's too bad. So knock out one of those terms. And then there is that augmented term, and then there's minus a term involving the distance to y of some perturbed thing there. So anyway, then, if you can show that the algorithm I gave earlier could be rewritten in the form of a proximal augmented Lagrangian type multiplier method, where I am going to, I still have the V's. I have the V's, okay. And I have the U's add up to 0, and I have a single Y. And now what I'm doing is I'm minimizing in this xj the augmented Lagrangian for that subproblem involving that shifted mapping F, and that's supposed to be just a Y nu. There's not supposed to be a J here on this Y. Nice thing about giving a talk is you can find your mistakes. And then because of the way this augmented Lagrangian is defined, you can show that this uj that you need is just the gradient in it. In many cases, you can write a formula for the gradient. And now, here's another thing that's playing into this. This elicitation had to do with second order theory, and somehow some kind of creation or discovery of convexity or monotonicity that's inherent in something. And with augmented Lagrangians, we know very well that they have a convexification effect. Augmented Lagrangians in the primal variables can create, and this is exactly, there's actually an equivalence in here, which I don't have time to explain. But this elicitation you can write in terms of being able to have an augmented, this is actually very general, not just this model, have an augmented Lagrangian such that you're looking at a local saddle point, a convex concave, locally convex concave saddle point of the augmented Lagrangian. This is going to be equivalent in some broad sense to this elicitation idea. So it again says that there's hope of getting it because we know augmented Lagrangians can do these things, and it's very basic to second order kinds of optimality. All right, now I just have these things. There's Spingarn's original paper in 1985 in which he had a method of decomposition, but he only did the convex case, and his R had to be 1 according to what I have, and he just was in a classical framework of convex programming also. Pennanen, on the other hand, developed a different idea of how you could use the proximal point algorithm without monotonicity, but he had a different way through a kind of a thing like Yoshida approximation to get some convexity. And it's sort of orthogonal to what I'm doing, but I think at some stage you'll be able to put them together for two purposes and get some advantage of it. Now, back in December, I wrote up a paper for a conference publication, and you never know what to put in a conference publication, but I wrote up a whole bunch of stuff in the convex case and put it in there with the knowledge that when I do the real thing, it would be covered anyway more generally. And then this was the hard thing I just finished a little while ago, this stuff about showing how a property called variational convexity, which is close to that thing I explained in the optimality condition, which has where you have a convex function that can do everything as well as the given function. And that corresponded to local monotonicity of the subgradient mapping. And then I'm almost done with writing up this, which includes the subject I talked about today. Okay, that's all. Thank you.